All right, so we're going to finish off this lesson. Then you have your quiz. So we have seen examples in the past where you can have an equation involving logarithms for different scenarios. In this case here, the relationship between the length s in meters of the skull of a dinosaur and the body mass m in kilograms can be expressed using the logarithmic equation given there. So this is used to compare the length of the skull of a dinosaur to its body mass. So S is the length of the skull, M is the body mass. Determine the body mass to the nearest kilogram of an Albertosaurus with a skull length of 0.78 meters. So we're just going to use that formula. 3.6022 log S equals log M minus 3.4444. And again, in this case, we're told that the skull length S is 0.78 of a meter. So we can get a value for the left side just by plugging that into our calculator. 3.6022 times the log, and this is a common log, no base indicated, so you can use the log key. And so that gives us a value for the left side, which is irrational because the log of 0.78 is an irrational number. We'll write it down rounded, but we'll keep the number in our calculator, so approximately negative 0.3887. And that'll be log of m minus 3.4444. So I will add that 3.4444 to both sides to get the log of m by itself. So we'll add 3.4444. And the log of m will equal that decimal, 3.0557. And the question then becomes, how do we find out what m is? What do you think, Sant? What would you do if this was a life or death situation for you? How?
So you take log 10, so take log 10 power, so it's 10 to the power 3.055.
Start with the base and cycle through. You just saved your life. A few more of you could have cheered about that.
You're alive still.
So again, we'll keep that number in our calculator, 10 to the power of the previous answer. Whoa. Try that again. So to the nearest kilogram, it would be 1,137 kilograms to the nearest kilogram. Okay? This next question then, what was the skull length of a T-Rex with an estimated body mass of 5,500 kilograms? So again, we start with that original formula. Only in this case, we're given m, the body mass. And we can find out what the right side is as an irrational number by taking the log of 5,500, close the bracket after the 5,500, and subtract 3.4444. Will give us 0.296, we'll say. But we're going to keep that number in our calculator, because now you have to find out what S is. And so in this case here, we would divide both sides by 3.6022 to get the log of S by itself. So we'll take that number and we'll divide by 3.6022. And that's what the log of S will equal, 0.0822. And again, we would solve for S by remembering that this is a common log, base 10. We'd start with the base and cycle through to get what S is. Yep. You have to close the bracket after 5,500.
Yeah, I did. I don't get that. 0.269. Oh.
Oh, I did. 0.295. So 10 to that power of the previous answer. So then there's hundredth of a meter, it would be 1.21 meters. Would be the length of that skull. Okay? When an animal dies, the amount of radioactive carbon-14 in its bones decrease. Archaeologists use this fact to determine the age of a fossil based on the amount of carbon-14 remaining. The half-life of that is 5,730 years. Head Smashed in Buffalo Jump is an actual place you can go to in southern Alberta. It's south of Calgary. It's recognized as the best example of a buffalo jump in North America. So what the First Nations people used to do is they used to chase the herd of buffalo towards this cliff, and the buffalo would fall off the cliff, and it was quite far down, and they'd hit the bottom, and then they'd die, and then they would go and they would harvest the meat. So they didn't have to try and hunt them this way. They would actually chase them off this cliff. That's what they actually did. So the oldest bones unearthed at the site had 49.5% of carbon-14 left. How old were the bones when they were found? So in this case, we're not given the equation, right? But essentially, we're going to use the, let me just get rid of some of this stuff. We're going to use the equation that is given on the formula sheet. So Let's open that up. The formula on the formula sheet that you're given for exponential growth and decay. Here it comes. Is this formula right here. Y equals A times B to the power T over P. So that's what we're going to use. Where A is the initial amount, B is the growth factor, T is the time, and P is the growth period. And if you look on the formula sheet, you're just given the equation. That's it. So you got to remember what all these variables mean. And the time and the growth period have to be in the same units. So in this case here, we're not given the initial amount, but we are told that the oldest bones found had 49.5% of the original carbon-14 left. So in this case here, Y, the amount at the end, will be 0.495 times A, the amount at the beginning. The growth factor in this case will be a half because we're told that the carbon-14 has a half-life of 5,730 years, which means that after 5,730 years, half of the original amount will be remaining. And then after another 5,730 years, half of what was left previously in the previous 5,730 years would be left. Our growth factor is a half because we are told that this has a half-life. And that is what P is. P is the growth period. How long it takes for there to be half of the original amount left. We want to find out what T is in this case. How much time has gone by so that there's 49.5% left. So our answer should be fairly close to 5,730, right? Because after 5,730 years, you'd have 50% left, because that's the half-life. So our answer should be something a little bit more than 5,730 years, because you're going to have 50% plus a little bit more, a 0.5% more. But we can find out exactly what it is by using that formula. So again, Y equals A times B to the T over P is what we're going to use. Y is the amount at the end, which is 0.495A. We'll keep A as the original amount, and then we'll be able to divide both sides by A to get rid of those variables. T is what we're looking for, and again, P is 5,730. So like I said, we can divide both sides by A, and they cancel. So now we're going to solve for T. And we can do that by converting from exponential to logarithmic, right? The exponential function on the right has a base of a half. So when you write it as a log, it'll be log with a base of a half. And to get the order that the other pieces go in, we start with the base and cycle through. So after the base of half, you're going to have 0.495 equals T over 5,730. Which you can get T by itself by multiplying both sides by the 5,730. So T will equal 5,730 times log base a half of 0.495. which we can do this in our calculator. So if you have the newer operating system, you can put that in all as one step. 5,730 times the log of 0.5, which is what a half is, of 0.495. And as we said, the answer is something a little bit greater than 5,730. It's 5,813 years. So T is approximately 5,813 years. Now, if you don't have the newer operating system, you have to use the change of base identity, right? So that would look like 5,730 times the log of 0.495, close the bracket, divided by the log of 0.5. So, same answer. Just have to use the change of base identity if you don't have the newer operating system. All right? So the rate at which an organism duplicates is called its doubling period. And so now you see the base is 2 because that's your growth factor. So sometimes you might be given the formula, at least part of it. In this case, you're given the base. You're given the 2, but it comes from the fact that it's a doubling period. So the general equation is n at t equals n sub 0 times 2 to the t over d. N is a number present after time t, n sub 0 is the original number, d is the doubling period, that's the growth factor, how long it takes for, in this case, for the organism to double, and t is the time. So E. coli is a rod-shaped bacterium commonly found in the intestinal tract of warm-blooded animals. Some strains can cause serious food poisoning. Supposed biologist originally estimates the number of these bacteria to be 1,000. After 90 minutes, there's 19,500. What is the doubling period? So we want to know what D is, the doubling period, if the time is 90 minutes. So again, if we start with this formula, which is n at t, the number at the end, equals n sub 0, which is a number at the beginning, times 2 to the power t over d. We're told the number at the end is 19,500. We're told we initially started with 1,000. And that the time is 90 minutes. Again, we want to know what d, the doubling period, is. So we can divide both sides by the 1,000 to get the exponential part by itself, which means on the left you're going to move the decimal spot 3 spaces over to get 19.5 equals 2 to the power 90 over d. And now to solve this again, we will convert from exponential to logarithmic. We'll start with the base and cycle through. So that'll give us log base 2 of 19.5 equals 90 over d. So let's get d by itself. If you multiply both sides by d, you'll get d times log base 2 of 19.5 equals 90. And then you would divide both sides by the log to get d by itself. So to the nearest minute, we can find out what that is by going 90 divided by, and then we'll use the log. Log base 2 of 19.5. So to the nearest minute, 21 minutes. Okay? Another application of this is compound interest. So, compound interest is different than simple interest. With simple interest, the interest is calculated once at the end of the term, but with compound interest, it's compounded and calculated at regular intervals. It might be compounded yearly, which means it's calculated every year, but then what happens is the interest is added to the principal, and then it just keeps growing, because the next time the interest is calculated, your principal goes up. You had your original principal plus the interest you gained in the last year. It gets added on, your principal's rising, so each time it's calculated, the amount of interest is growing. So your investments grow a lot faster with compound interest. But it's not always calculated annually. Sometimes it's calculated semi-annually, which is twice a year. Or it might be calculated quarterly, which is 4 times a year, every 3 months. Or it might be calculated monthly, or it might even be calculated daily. So you need to know all that, right? And so the graph just kind of shows how the different compounding periods affects the growth. You can see that the highest growth occurs when it's compounded continuously, like daily. Okay, it grows a little bit less quickly if it's monthly or quarterly or even yearly. So the more often it's compounded, the faster the money grows. All right. So again, compounded periods can be annually, which is once a year, semi-annually, twice a year, quarterly, 4 times a year. It could be monthly, it could be weekly, it could be daily. Now we do have a compound interest formula, but it's not given to us on the formula sheet. So instead, we will use the y equals a times b to the t over p, the same formula that is on the formula sheet. Okay, and if you look at these, and you compare them, P is the principal, that's the original amount. Well, that's what A represents with our equation, the initial amount. The 1 plus I is your growth factor, your growth rate, okay? And that's what B represents, your growth rate, or your growth factor. And then instead of N, it's T over P. T is the time, P is the growth period. And that's the same thing as N using the compound interest formula, right? So we'll see how we use this formula to answer these types of questions. So this first example says that $5,000 is invested into a 7-year GIC. So GIC is a guaranteed investment certificate. Basically, the bank will guarantee that you're going to have that interest rate for the length of the investment, which in this case is 7 years. So it's compounded quarterly at 3.5% per annum. So per annum means per year. So that is the yearly interest rate, but it's compounded quarterly, which is 4 times a year. Determine the value of the investment at the end of the term. So after 7 years, what is it worth? So when we use this formula, y equals a times b to the power t over p. So A is the initial amount, which is $5,000. B will be the growth factor. Okay, so to calculate B, here's what we need to do. The annual rate is 3.5%, which is 0.035, but that is the annual rate. This is compounded quarterly, which is 4 times a year. So we have to take that and divide it by 4. So that's the first step to finding B. 0.035 divided by 4 is that decimal. But what you have to understand is that we also need to add 1 onto that, because your money is growing. You're going to have 100% of what you had from the last quarter plus this decimal more. And so because you have 100% plus this decimal more, you add 1 onto that. The 1 represents 100% of the money you had before, plus the amount you're going to get from this interest rate. Okay, so that will be 1.00875. That is B, our growth rate. T is the time. Whoops. T is the time, which in this case would be 7 years. And P is the growth period. All right. And what's happening here is that the interest is calculated quarterly, which is every 3 months. Remember, we said that T and P have to be in the same unit. So we will convert our 7 years into months by multiplying that by 12, which is 84. This interest is being calculated quarterly, which is every 3 months. So in the first year, it'll have happened 4 times. In the second year, now it will have done 8 times. So over 7 years, it will be calculated 28 times. And the way you get that number 28 from is by dividing the 84 by the 3, because the formula says it's T divided by P. So you can get what the power, the T over P value is, just by using some logic like I just said. It's compounded quarterly, which is 4 times a year. So 4 times in the first year. In the second year, that'll be 8. In the third year, that'll be 12. 4 times a year for 7 years, you'll get 28 as the exponent. But we're going to get that when we divide the 84 by the 3. So our equation will be y equals A, which is 5,000, times our growth rate, which is 1.00875, to the power 84 over 3, which, as we said, will give us our 24 or 28 times. So 5,000 times 1.00875 to the power 28, which you can put in your calculator all in one step. So 5,000 bracket 1.00875 to the power 28 is the value of the investment. So it started with 5,000, now it's 6381.30. There's the value of that investment. Yeah. So there you're going to subtract the $5,000 from that. I, the interest, would be the difference between what you ended up with and what you started with. So that'll be 1381.30. Okay. So the next question, Kelly invested $2,500 for 4 years, compounded semi-annually, and received $843.26 in interest. What was the annual interest rate? So if we start with that general formula again, y equals A times B to the power T over P. Remember that y is the final amount. In this case, y would be found by taking the amount you started with and adding the interest. Y is 3343.26. B is the beginning amount, which is 2,500. T is the time, which we'll say now, for now, is 4 years. But P is the growth period. And in this case, it's compounded semi-annually, which means every 6 months. But remember, these two have to be in the same unit. So 4 years would be 4 times 12, which is 48 months. And when you go T divided by P, 48 divided by 6 is 8. The interest is going to be calculated 8 times. And if you think about it, twice a year for 4 years. That's where that 8 comes from. So we need to find out what B, the growth rate, is. So plugging into our equation, our Y value is 33, 43, 26. That equals A, which is 2,500, times B to the power T over P, which we knew was going to be 8. You could get that logically or by dividing the T and the P together. But the other thing we can do here is we can divide both sides by the 2,500 to get the exponential part by itself. So 33, 43.26 divided by 2,500, 1.337304. Equals B to the power 8. So to find out what B is, we would have to take the 8th root of both sides, the 8th root of both sides, because that is the opposite of power 8. And that'll give us what B is. So 8, math, 5 is the x root. So the 8th root of the previous answer is that number there, 1.037. Well, not quite. Remember, the 1 stands for the 100% plus 0.037 more. So we first get rid of the 1 because the 1 represents the 100%. So the semi-annual rate, because it's being compounded semi-annually, the semi-annual rate will be found by taking the 1.037 and subtracting the 1. The semi-annual rate would be 0.037 or 3.7%. So now the annual rate will be found by, yes, multiplying by 2. Which will give you 7.4% is the annual rate. Okay, we're going to look at example 3, and then we're going to stop there. We'll do a few more of these on Tuesday, as well as going through the quizzes. But I want to make sure you have lots of time to do this quiz, so we'll stop after this one. George invests $3,000 in an account which pays compounded interest at 5.3% per annum, but it's compounded monthly. How long would it take for this investment to double? So using the formula, y equals a times b to the t over p. Remember, y is the amount at the end. If you start with 3,000 and you want it to double, you're going to end up with 6,000. A is the initial amount, which is our 3,000. Define B, our growth rate. Remember, we're going to add 1 to the decimal we get, which will represent 100% of it, plus the annual rate is 5.3%, which is 0.053, but because it's compounded monthly, we have to divide that by 12. So 0.053 divided by 12 plus 1 is 1.0442 if I round it. Now I'm going to keep that number in the calculator, store it into memory slot A. But to round it down, I'm going to put 1.00442. We're trying to find out what T is. How long will it take for the investment to double, If P, the growth period, is 1 month, because it's compounded monthly. So we're going to find out what T is, and it'll be the number of months, because P is in months. So Y is 6,000, A is 3,000. Our B is 1.00442, and again, that's a rounded value. We'll use the entire decimal that's in our calculator when we need it, to the power T over 1, which is just T. And T will be the number of months. So if you divide the 3,000 on both sides, you'll get 2 on the left, equals 1.00442 to the power T. And then to find out what T is, we will convert from exponential to logarithmic. The log with a base of 1.00442 of 2 is what T will equal. So to the calculator we'll go, and using our log function, it will be the log of the previous answer, that's my alpha A, of 2. So we get 157.3 months, which we would have to round up to 158, because if you round it down, there won't be $6,000 there. So they're writing a quiz in that room over there. Yeah.
Okay,
But I'll take it from them soon, because just give me 2 minutes.
sure, yeah.
Yeah.
Whenever you're done, you send them down the science on.
Yeah. Okay, so if you round it down, there's not going to be $6,000 there. So you have to round this up. So the amount is going to be a little greater than 6,000, but at least it's going to be at least double. So you have to round this up to 158 months. Which is what it asks us for, the number of months. Okay? So yes, we'll stop there. We'll do a few more examples of these on Tuesday.